Assalamualaikum and hi everyone. Today we will continue with single phase full wave rectifiers. So here we will cover uncontrolled full wave with R load and RL load, and then control full wave rectifier with R load and RL load as well. Okay, in a half-wave rectifier, the output amplitude is less than the input amplitude, right? And there's no output during the negative half cycle. So half of the power has been wasted and the output is pulse DC, resulting in excessive ripple. Okay, so to overcome this problem, a number of power diode can be connected together to produce a full wave rectifier. Okay, so as you can see here, we have 2 diode in the circuit or 4 diode for the full bridge circuit here. Okay, and the objective of this full wave rectifier is actually similar to that half wave rectifier, in which to produce a voltage or current which is purely DC or has some specified DC component. Okay, and the advantage of this full wave rectifier is the output has less ripple than the half wave rectifier and no power is wasted. There are two types for a single phase full wave rectifier. Okay, so here we have a center tap transformer rectifier. Okay, so for center tap we have 2 diode only, and then we also have a bridge rectifier, or also known as a full bridge. Okay, so for a full bridge we have 4 diode. Okay, so this is the basic diagram which also can be represented by this circuit. Okay, a center tap rectifier requires a center tap transformer, but bridge does not. So this is the center tap transformer. Okay, so what is the function of this transformer? Okay, so it is used to provide an electrical isolation between the source and the load. Okay, so if something happened at the load, the power supply is safe and vice versa. Okay, and just like I've mentioned before, a center tap rectifier requires only 2 diode. Okay, so we have D1 and D2. Okay, but per half cycle only 1 diode is function. Okay, so if D1 is on during the positive half cycle, D2 must be off and vice versa. Okay, and then because of it has an electrical isolation, it is suitable for low voltage and high current applications. Okay, for a center tap rectifier, as I've mentioned just now, if D1 is on, so D2 must be turned off, right? Okay, so during the positive half cycle, the current will flow through D1 and then go to the load. Okay, so when D1 is on, there will be no voltage drop at D1, but there will be a voltage drop at D2. Okay, so there will be an output current for D1 as the current flow here. Okay, and there will be no output current for ID2. Okay, and then during the negative half cycle, okay, so now D2 is on and D1 must be turned off, right? Okay, so how is the current flow? The current will flow through D2 and then goes to the load. Okay, so now there will be a voltage drop at D1 but 0 voltage drop at D2. Okay, but for the current, there will be an output current for D2 as the current flow here. Okay, and there will be 0 output current for D1. Okay, so for a center tap rectifier, for a full wave rectifier, there will be an output current for both positive cycle and negative cycle, as there's a diode conducting during both cycle. Okay, so the output current is given by ID1 plus ID2. Okay. Okay, for a full bridge rectifier, okay, there will be 4 diodes. So we have D1, D2, D3 and D4. Okay, so during the positive half cycle, D1 must be operated with D2. Okay, so when D1 and D2 is on, D4 and D3 must be turned off and vice versa. So in one time only 2 diodes can be operated. Okay, so D1 works with D2 and D3 with D4. Okay, so during the positive half cycle, the current will flow through D1 and then goes to the load and then D2 and go back to the source. Okay, so that one is during the positive half cycle. Okay, now during the negative half cycle, so what happened? Okay, so during the negative half cycle, the current will flow through D3 and then to the load and then to D4 and then go back to the power supply. Okay, so the voltage across the load is positive when D1 and D2 are on, and it is negative when D3 and D2 are on. Okay, and this full bridge rectifier is suitable for high voltage applications as it has a lower power diode voltage. Okay, so for a full bridge rectifier, when D1 and D2 is on, okay, there will be no voltage drop at D1 and D2, but there will be a voltage drop at D3 and D4. Okay, and there will be an output current at D1 and D2, and D3 and D4 is 0 as the current now flow like this. Okay. Okay, then when D3 and D4 is on, okay, so this is during the negative half cycle, so the current will flow through D3 and then to the load and then to D4 and then go back to the source. Okay, so now there will be an output current for D3 and D4 while D1 and D2 is 0. Okay, so finally, as you can see here, the output current, there will be an output current during the negative half cycle and also during the positive half cycle. Okay, so it is continuous now. Okay, for uncontrolled full wave RL load, the analysis method is actually similar to that half wave rectifier. But for the bridge circuit, okay, a current is transferred from one pair to the other pair when the source is changing polarity. So again, if D1 and D2 is on, okay, so D3 and D4 must be turned off. Okay, and vice versa. Okay, so here as we have RL load, due to the inductance load, the output current increase slowly, okay, during the first half cycle, and the larger the inductance, the larger the delay, or it becomes slower. Then before the current reach 0, okay, reach 0 here, D3 and D4 is on. So D3 and D4 is on. Okay, so finally we will get the output current continuous like this. Okay, where I out is given by ID1 plus ID3, which is also equal to ID2 plus ID4. Okay.